Hello everybody, welcome to the 9th online Excel module for ManEc/Fin 453. Today we'll be doing a matrix algebra primer and we'll also be talking about portfolio optimization. You can see from the map here, last module was the residual income model, so today we pick up with matrix algebra, and I'm also going to include portfolio optimization. So I have good news and bad news related to this 9th Excel module. The good news is that there won't be any deliverables associated with the module. The bad news, however, is that this is going to be a very long and involved module, and you certainly don't want to skip it. The reason for that is the ultimate goal over the next 3 modules is to get you to the point where you can map out the efficient frontier using more than 2 assets. This involves, of necessity, executing portfolio optimization with more than 2 assets, and it turns out that that's a skill that not very many programs teach to their undergraduates because it does require a knowledge of matrix algebra, which is a skill, a mathematical skill that most undergraduates in business programs have not been asked to acquire. So I'm going to try to build you up to it. I'm going to give you the necessary matrix algebra skills, and we're going to try to get you there over the next 3 modules, but you are going to have to pay attention, and it is going to take a lot of concentration and effort on your part. So you can see where we're headed now for the next few modules is to actually work on array and matrix functions. My goals for Excel module number 9 is to teach the basics of simple matrix algebra mathematical operations, and then I want to demonstrate how matrix algebra can be used to calculate the expected return and the standard deviation of a portfolio. And I would also like to explain how to use some of the matrix operators in Excel. So when we think of portfolio optimization, at least mean variance portfolio optimization, what we're talking about are 2 components, reward and risk. When we try to quantify reward and risk, there are various ways of doing so, but for our purposes, we're going to quantify reward simply as the average expected return, and we're going to quantify risk as total risk, so that's going to be standard deviation of returns or the dispersion in average returns. So return will just be expected, or reward will just be expected return, and risk will be the standard deviation of returns. Now, just to try to lead into the discussion, when you analyze these 4 exchange traded funds that exist, I've put on here the annual average return over the last several years along with the standard deviation of those returns. So the question is, which of those 4 assets would you prefer? Now, some of you would say, well, I want the expected return or the average return at 19%. But some of you would be turned off by the 20.84% standard deviation. Some of you might be more inclined to take the lower expected return if it also gave you the lower standard deviation. The key point being both average return and dispersion matter. You can't separate them. So when we talk about mean variance portfolio optimization, there are actually 3 possible definitions. The first definition is that we could maximize a portfolio's expected return given a set level of acceptable dispersion or volatility. In other words, you set the dispersion or the standard deviation, and then you try to maximize the return at that set level of standard deviation. The second possible definition is to minimize a portfolio's dispersion or volatility given a set level of desired expected return. So in this instance, you lock in the expected return that you're aiming for, and then you try to achieve the lowest standard deviation associated with that expected return. The third possibility is that we could try to maximize the ratio of the expected return to the dispersion or volatility. Now this has a name, it's called the Sharpe ratio. So the third definition of portfolio optimization is simply maximizing the Sharpe ratio. We remember from previous instruction that the expected return of a portfolio is simply the weighted average of the expected returns to each of the assets in the portfolio. So if we assume a portfolio consists of only 2 assets, and if expected return 1 and expected return 2 represent the expected returns to those 2 assets respectively, and if we assume that W1 and W2 are the portfolio weights, then the portfolio expected return can be represented this way. It's simply the weight of asset 1 times the expected return of asset 1 plus the product of the weight of asset 2 times the expected return of asset 2. This formula is easily expanded to include more than 2 assets. So assume that a portfolio, instead of consisting of only 2 assets, now consists of K assets. If the expected return I is used to denote the expected return to asset I, and obviously I can be 1 through K. And if we also say that WI is the weight of the total portfolio invested in asset I, then we can represent the portfolio expected return thusly. It's merely the sum of the products of each of the weights and the expected returns. We can shorten the mathematical representation thusly. Again, it's just the sum of the product of all of the weights against the expected returns. Now, the portfolio standard deviation is a bit more involved. Why is it that portfolio standard deviation is more complex to calculate than expected return? The answer is because the dispersion of a portfolio will be influenced by 3 variables. Now, the expected return was only influenced by 2, weights and expected returns. But the standard deviation is actually influenced by weights, the individual standard deviations, and also the co-movement between the assets in the portfolio. Generally speaking, we can say that the more assets prices move in opposite directions, the less the total dispersion in the portfolio as a whole. For instance, take a look at this graph. The bright yellow line near the bottom represents price movements in Home Depot. The brown line represents price movements in an exchange-traded fund that holds Treasury securities. The black line represents price movements in the price of target stock. Now, my question is this. If you were thinking about combining an asset with Target, so you own the black line, then which asset would help you the most in reducing your portfolio standard deviation? Would combining Home Depot, which is the yellow line, or would combining the Treasury's ETF, which is the brown line, which one of those combinations with your already held target stock would give you the lowest portfolio standard deviation? Well, I've tried both, and here's the result. The black line is the target stock. That was the original stock that we started with, and then we were either adding Home Depot or adding a Treasury ETF. Well, the white dotted line represents a portfolio that is comprised of both Target and Home Depot. The red line represents a portfolio that is a combination of Target stock and the Treasury's ETF. What we take from this is that combining Target stock with the Treasury's ETF provides a much less volatile, much smoother portfolio than combining Target with Home Depot. What I mean is that the red dotted line is clearly less volatile than the white dotted line. Well, the reason for this is obvious. It's because the yellow and the black line in this chart tend to move together, so you don't get much diversification benefit. However, the black line and the brown line tend to move in opposite directions, which means there are potential advantages to be had in terms of mitigating risk by combining those 2 assets, which is what we see. Mathematically, if we want to define the standard deviation of a portfolio, we use the following nomenclature. So we'll use WI to represent the weight of portfolio invested in asset I. Sigma I is the standard deviation of asset I. Sigma II will be the same thing as the variance of asset I. Sigma ij will be the covariance between asset I and asset j. And rho ij will be the correlation between asset I and asset j. Also, remember that the correlation ij, so rho ij, is simply the covariance over the product of the standard deviations. And lastly, rho ij is bounded by -1 and 1. Employing that nomenclature where we have only 2 assets, the portfolio standard deviation is defined thusly. It is the square root of W1 squared times the variance of asset 1 plus W2 squared times the variance of asset 2 plus 2 times W1 times W2 times the covariance of assets 1 and 2. Now, please note, as we mentioned earlier, portfolio standard deviation is a function of 3 factors: the portfolio weights, the standard deviations of the individual assets, and the co-movement between the prices of the two assets. Now, we could represent this same equation slightly differently, since the correlation coefficient, or rho ij, is the covariance over the product of the standard deviations. We could replace the covariance with rho ij times the product of the standard deviations. So we can make that replacement. We can replace the covariance with rho times the product of the standard deviations, and it's still the same formula. Where there are three assets, portfolio standard deviation is as shown below. So it's the square root of W1 squared times sigma 1 squared plus W2 squared times sigma 2 squared plus W3 squared times sigma 3 squared plus 2 times W1 times W2 sigma 1 2 plus 2 times W1 times W3 times sigma 1 3 plus 2 times W2 times W3 sigma 2 3. That is not just a mouthful, it's also an eyeball full. And so we can see that the formula quickly becomes unwieldy as the number of assets grows. Now, the general formula for k assets is as shown below. It's the square root with two summation indexes of wi times wj sigma ij. And what you would have to do is you would have to work through each of the counters. But if you work through this formula for a three-asset portfolio, this is the result. Now, I don't expect you to memorize that, but we will come back to that later. Now, it turns out that since this math gets so unwieldy, nobody wants to type this in by hand into Excel. Mercifully, we can employ principles of matrix algebra to incredibly expedite the process of executing this math. I'm showing you this to try to motivate the next half hour. The next half hour has the potential to be boring because I'm going to show you matrix algebra. It's going to be a math lesson. But the reason I'm showing it to you is to prove to you that you don't want to do this math by hand. If there's any way to expedite it, we want to expedite it, and we can use matrix algebra to expedite it. And by the way, isn't that the best way to learn math anyways? Let's figure out why we would want it in the first place, and then let's figure out the tool to make it happen. So, let's start with some basic definitions when it comes to matrix algebra. First definition, a scalar is a single number. A vector is a single column or a single row of numbers. A matrix is a system of numbers containing multiple rows and columns, usually denoted by uppercase letters algebraically. As a note, we can define vectors and matrices as n by k, where n represents the number of rows and k represents the number of columns. As an example, a scalar would be the number 7. It's a single number. A vector is a single row or column. So right here we have a 4 by 1 vector. It has 4 rows but a single column. This conversely represents a 1 by 4 vector, a single row but 4 columns. Over here we have a 3 by 4 matrix with 3 rows and 4 columns. So typical matrix notation can be presented thusly. If we have an X matrix that is n by k, so it has n rows and k columns, we can identify this element x23 because it is in the second row and third column. Using our previous matrix then, our 3 by 4 matrix, we can define each element. We can define the element in the first row, first column, first row, second column, all the way down to the third row, fourth column. Now please note, I'm only showing the dimensions of the matrix for expositional purposes. Normally we would not put these numbers right here after the x variable denoting the matrix. Now there is a principle called transposition. How do we transpose a vector? To transpose a vector means that the single row becomes a single column and vice versa. For instance, if we have a 4 by 1 vector and we want to transpose it, so if we call this vector z, then we would do z with a capital T. That represents z transpose. So z transpose, that row would then become the column. So instead of having a 4 by 1 vector, we would now have a 1 by 4 vector. Transposing a matrix means that the columns become the rows and the rows become the columns. So if we have a 3 by 4 matrix, transposing it means that this first row would turn into our first column. This second row would turn into our second column, and this third row would turn into our third column. Therefore, the dimensions of our original matrix, which is 3 by 4, would flip, and X transpose would be a 4 by 3 matrix. So you can see that the first column has been transposed into the first row, second column, second row, third column, third row, fourth column, fourth row. You can also see that the dimension of the matrix is flipped. Now let's talk about basic matrix operations. Whenever a mathematical operation is performed involving a scalar and a vector or matrix, then the vector or matrix retains its dimensions. The scalar is operated against all individual components of the vector or matrix. So if you have a scalar, which is a single number, and you're operating against a matrix or a vector, then the matrix or vector retains its dimensions, and you simply multiply the mathematic operation against all elements of the matrix. For instance, y plus x would be executed thusly. Each element of the X matrix would have y added to it. This same basic procedure is followed for subtraction, multiplication, and division. So, for example, if y equals 4, and we have our 3 by 4 matrix that we've been using, then to take x plus y, you would simply add 4 to every single element in the matrix, and the matrix would retain its original dimensions. Similarly, if y was now equal to 2, and we wanted to multiply the scalar y by the X matrix, we would just multiply every single element of the matrix by 2. Again, the matrix would retain its 3 by 4 dimensions. Whenever adding or subtracting entire matrices, the two matrices must have the same dimensions. The operation is then executed simply on the matched individual components of the two matrices. So for instance, if we have an X and a Y matrix, both 2 by 2, if we wanted to add the X and Y matrices, you would simply add the elements. So x11 would be added to y11, and that would give you the first element of the new matrix. Similarly, if you wanted to get the element in the first row, second column, you would take x12 plus y12, and so forth. So for example, if we have an X matrix as shown here, and a Y matrix also as shown here, and we wanted to add the X and the Y matrix, then we would just add 3 to 1, 4 to 6, 7 to 5, 2 to 9, and the resulting matrix would look like this. Matrix multiplication, unfortunately, is a bit more complex. There are two important rules when it comes to matrix multiplication. Rule number 1, two matrices can only be multiplied if the number of columns in the first matrix is equal to the number of rows in the second matrix. Rule number 2, when two matrices are multiplied, the resulting matrix will have the same number of rows as the first matrix and the same number of columns as the second matrix. For example, if X is a 3 by 4 matrix and Y is a 2 by 4 matrix, these two matrices may not be multiplied as xy because 4 does not equal 2. In other words, the number of columns in the first matrix does not equal the number of rows in the second matrix. So that would be a violation of rule number 1. However, X and the transpose of Y may be multiplied because X, Y transpose meets the criterion set forth in rule 1. Specifically, the number of columns in X matches the number of rows in Y transpose. So if you actually did multiply X, Y transpose by rule number 2, the resulting matrix would be a 3 by 2 matrix because rule number 2 says that the resulting matrix, when multiplying two matrices, will have the number of rows from the first matrix and the number of columns from the second matrix. Now, how do we actually execute matrix multiplication? Well, let's consider a 2 by 3 matrix being multiplied against a 3 by 2 matrix. This works because the number of columns in the first matrix equals the number of rows in the second matrix, so rule number 1 is satisfied. By rule number 2, when we multiply these two matrices, the resulting matrix will have 2 rows and 2 columns. So the resulting matrix will be a 2 by 2 matrix. And the way that we do this is to get, so let's call the resulting matrix Z. And the way that we get the first element, so element 1, 1 in the Z matrix, is to take the first row from the first matrix and multiply it by the first column of the second matrix. So we would take row 1 from the X matrix and multiply it by Y1, or by the, so we would take row 1 from the X matrix and multiply it by column 1 from the Y matrix. In order to get Z12, we would take the first row from the X matrix and multiply it by the second column from the Y matrix. In order to get element Z21, we would take the second row from the X matrix and multiply it by the first column in the Y matrix. Lastly, to get element Z22, we would take the second row from the X matrix and multiply it by the second column from the Y matrix. What that means is this. In order to get element 1, 1, we take row 1 from X and multiply it by column 1 in Y. So you would take X11 times Y11 plus X12 times Y21 plus X13 times Y31. So you would add up those products, and that would give you element 1, 1. For instance, to get element 2, 2, you would take the second row times the second column. X21 times Y12 plus X22 times Y22 plus X23 times Y32. Add up those products, and you would get element 2, 2. So this is how you execute matrix multiplication. Let's do a real-world example. So if we have a 2 by 3 and a 3 by 2 matrix, and here are the numbers in those matrices, we're going to multiply these two matrices to give us a Z matrix, which is going to end up being 2 by 2. And the way that we get the elements is just as I described in the previous slide. So to get the first element, Z11, we would take 3 times 1 plus 6 times 2 plus 8 times 6. So here it is, 3 times 1 plus 6 times 2 plus 8 times 6, which results in 63. In order to get element 1, 2, we would take first row, second column. So 3 times 8 plus 6 times 7 plus 8 times 3. There you have it. In order to get element 2, 1, we would take the second row, first column. 2 times 1, 4 times 2, 5 times 6. Add up those products, and it gives us element 2, 1. In order to get element 2, 2, we need second row, second column. 2 times 8, 4 times 7, 5 times 3. Add up the products, and we arrive at 59. So now that I've shown you in PowerPoint how to do these very simple matrix operations, I'd like to show you very quickly in Excel how easy it can be. So just as an example, make these a little bit bigger. So just as an example, I have a vector 2, 8, 3, 5. That's a 4 by 1 vector. If we wanted to transpose it, we would turn it into a 1 by 4 vector. What you would do is simply this. Highlight where that vector is going to go. So that's a 1 by 4 space. Hit the equals sign. Type in transpose. Highlight that vector. Here's the key though in Excel. Anytime you're doing any sort of matrix operation, you must hold down Control and Shift when you hit Enter. So Control, Shift, Enter, and you can see it's transposed this for us. If you fail to hold down Control and Shift, this is what will happen. Error. So remember, anytime you're doing matrix operations, you've got to hold down Control and Shift while you hit Enter. We could also transpose this matrix. Right now it's a 3 by 4. That means if we transpose it, it would be 4 by 3. So it's the same process. You can transpose it like this. Control, Shift, Enter, and you can see that the first row has become the first column, second row has become second column, third row has become third column. Now we can also add. So what if we wanted to add this scalar to this matrix? Remember, it would retain its dimensions. So we would have a 3 by 4 matrix. We just type in the scalar, add it to this whole matrix, but remember, Control, Shift, Enter, and you can see that it has operated 4 throughout the matrix. Likewise, we can multiply. So what if we wanted to multiply 2? So if we wanted to multiply 2 through the whole matrix, it would retain its dimensions. So we would go and click on 2, multiply it by the entire matrix, Control, Shift, Enter, and there it is. What if we wanted to add these two matrices right here? They're both 2 by 2, so we can do it. The resulting matrix would also be 2 by 2. So we would take that matrix plus that matrix, Control, Shift, Enter, and you can see that it has taken 3 plus 1, 4 plus 6, 7 plus 5, 2 plus 9. Now, what if we wanted to multiply this 2 by 3 matrix against this 3 by 2 matrix? We know that it works. This is 2 by 3. This is 3 by 2. So the columns in this matrix are the same as the rows in this matrix. That satisfies rule number 1. And that also means that our resulting matrix will be 2 by 2. So we highlight a 2 by 2 region. We type in matrix multiply, highlight the first matrix, highlight the second matrix, hit Control, Shift, Enter, and you can see that we get the exact outcome that was shown to us in the PowerPoint slide. 63, 90, 40, 59, and so we have it. So okay, that's your very brief matrix algebra primer. Now obviously there's a lot more to understand about matrix algebra, but that's all you need in order to execute portfolio optimization. So what I'd like to do for the next 10 or 15 minutes is demonstrate to you how matrix algebra can be incredibly helpful in expediting the execution of portfolio optimization. Let's begin by exploring how matrix algebra can expedite our calculation of portfolio expected return. So again, assume you have a portfolio that's comprised of k assets. Define two k by 1 vectors. We'll call this a W vector. It just contains the weights of each of the k assets in our portfolio. We'll also define a mu vector, which is the expected return of each of the assets in our portfolio. In order to obtain the expected return of our portfolio, which we defined earlier thusly, it's very simple. All we have to do is take W transpose and multiply it by mu. If we transpose W, instead of being a k by 1 vector, it turns into a 1 by k vector. We still have our mu vector, which is k by 1. Therefore, W transpose mu is a 1 by k multiplied against a k by 1. We can do this because the number of columns in the first vector equal the number of rows in the second vector. So rule number 1 is satisfied. Rule number 2 then tells us that the result of this multiplication will simply be a 1 by 1 matrix, which is the same thing as saying a single number or a scalar. So literally, W transpose mu would just be what? Row 1 multiplied by column 1. W1 times expected return 1, W2 times expected return 2, W3 times expected return 3, all the way down to WK times expected return k, and we would add all that up to arrive at our scalar. So literally, In order to get portfolio expected return, all you have to do is take W transpose mu. Just as an example, let's assume we have a 4-asset portfolio with the following weights. TLT is 10%, LQD is 25%, GLD is 30%, and EEM is 35%. So these are 4 different assets in our portfolio. Now let's assume that they have monthly average returns as outlined right here. So those are the average monthly returns. My question is, how can we get the portfolio expected return? Well, we define our W vector, which is just the weights, our mu vector, which is the average monthly returns, and then we simply take W transpose mu. So we turn this, instead of a 4 by 1 vector, we turn it into a 1 by 4 vector, and then we just multiply element by element to get our portfolio expected return. This is easily executed in Excel. And again, let me enlarge this just a little bit. So here is our W vector. That's our weight vector. Here's our mu vector. What we're going to do is take W transpose. So W transpose, instead of being 4 by 1, will be 1 by 4. So we're going to take W transpose and multiply it by mu. That's going to result in a scalar, so we can simply do this. Matrix multiplication, take the transpose of my W vector, multiply it by my mu vector, close up the parentheses. Now remember, any time you do matrix multiplication, you must hold down Control, Shift, Enter as you do this. Turn it into a percent, and we get our portfolio expected return. So just to prove this to you, what would have been the more laborious method of actually figuring it out? Well, you could have done this. You could have said, well, I need to take weight times mu for every single asset, and then I need to add all those up. That's the long way of getting there. And you can see that as we do the long way, we get the exact same answer as we got when we did matrix multiplication. So what I'm trying to get you to understand is this matrix multiplication, the only reason we're talking about it and the only reason we care about it right now is because it can make things go a lot faster for us. Now, how can we use matrix algebra to get the portfolio standard deviation? We'll begin with a 3-asset portfolio to demonstrate. And what you have to do is to define a vector and a sigma matrix. So if we're doing a 3-asset portfolio, define your W vector just as we did previously. So the W vector contains the weights of each of the assets in your portfolio. The sigma vector contains the variances and covariances between the 3 assets. On the diagonal, we find the variances. Remember, sigma 1, 1 is the same thing as sigma 1 squared. Sigma 2, 2 is sigma 2 squared. Sigma 3, 3 is sigma 3 squared. So on the horizontal, on the diagonal, we have the variances. On the off diagonals, we have the covariances. So the covariance of 1, 2, 1, 3, covariance 2, 1, which is the same thing as covariance 1, 2. Covariance 3, 1, which is the same thing as covariance 1, 3, as we described earlier. Covariance 3, 2, which is the same as covariance 2, 3. The standard deviation of a 3-asset portfolio, as we defined earlier, is represented mathematically right here. So we want to see if matrix algebra can get us to land at this formula and hopefully get us there a lot more quickly. Well, it turns out that we can actually obtain this exact formula using matrix algebra if we simply do this. W transpose sigma W, and we take that to the 1/2. Because if you think about it, here's W transpose, here's our sigma matrix, and here's our W vector. That's 1 by 3, 3 by 3, 3 by 1. So if we take a 1 by 3 and multiply it by a 3 by 3, those two together will result in a 1 by 3 vector. If we take a 1 by 3 vector and multiply it by a 3 by 1 vector, we get a scalar. Take the square root of that and we have standard deviation. Let me try to demonstrate this to you. Stay with me. This is where it gets a little bit ugly. So first off, let's take W transpose sigma. So W transpose sigma is a 1 by 3 vector multiplied against a 3 by 3 matrix. It's going to result in a 1 by 3 vector. How do we do it? Well, in order to get element 1, 1, we take row 1 times column 1. In order to get element 1, 2, we take row 1 times column 2. In order to get element 1, 3, we take row 1 times column 3. So it would look like this. For element 1, 1, it would be 1, so weight 1 against sigma 1, 1, weight 2 against sigma 2, 1, weight 3 against sigma 3, 1, add up the products. To get element 1, 2, we take row 1, column 2. So weight 1, sigma 1, 2, weight 2, sigma 2, 2, weight 3, sigma 3, 2, add up the products. In order to get element 1, 3, we take row 1, column 3. So weight 1, sigma 1, 3, weight 2, sigma 2, 3, weight 3, sigma 3, 3, add up the products. So W transpose sigma results in this 1 by 3 matrix. We now need to take this 1 by 3 matrix and multiply it against the W vector. So we take W transpose W, which we arrived at earlier, and we now multiply it against this W vector. This is a 1 by 3 vector against a 3 by 1 vector. That's going to result in a scalar. So all we have to do is take first row against first column. So we take this first element and multiply it by this first element over here. So W1 multiplies through those brackets. We take the second element and multiply it by W2. W2 then multiplies through the bracket. We take the third element, multiply it by W3, so W3 simply multiplies through the bracket. If you multiply through all the brackets, if you distribute the math, it ends up being this. W1 squared, sigma 1, 1, which remember that's the same as the variance of sigma 1. W1, 2, sigma 2, 1. W1, 3, sigma 3, 1. W2, W1, sigma 1, 2. W2 squared, sigma 2, 2, which is again just the variance of sigma of asset 2. W2, 3, sigma 3, 2. W3, W1, sigma 1, 3. W3, W2, sigma 2, 3. And W3 squared, sigma 3, 3, which is the variance. Now, we can actually combine some of these. For instance, W1, W2, sigma 2, 1 happens to be the same thing as W2, W1, sigma 1, 2, so those can be combined. W1, W3, sigma 3, 1 happens to be the same as W3, W1, sigma 1, 3, so we can put those together. W2, W3, sigma 3, 2 also happens to be the same as W3, W2, sigma 2, 3. So when we actually combine everything that we can combine, W transpose sigma W actually becomes W1 squared, sigma 1, 1, W2 squared, sigma 2, 2, W3 squared, sigma 3, 3, 2W1, W2, sigma 1, 2, 2W1, W3, sigma 1, 3, 2W2, W3, sigma 2, 3, and then when we take the square root of it, we arrive at the original formula that we laid out at the beginning of this presentation, which is the standard deviation of a 3-asset portfolio. The general result, which is meant to be the punchline of this entire module, is instead of doing this very ugly math right here, we can simply do W transpose sigma W and take the square root of that, and we can get the portfolio standard deviation. Much, much quicker and cleaner than executing this math. And the good news is we can ratchet that up. We can have 10 assets in our portfolio and this will still work. Can you imagine what this would look like if we wrote it out for 10 assets? So I'd like to show you this for a real portfolio. So here's our portfolio of 4 assets using the same weight matrix that we used before. And now I have calculated the variance-covariance matrix. So here it is. We still need to talk about getting the variance-covariance matrix. But that's the variance-covariance matrix right there. All we have to do in order to get portfolio standard deviation is take weight W transpose, multiply it by sigma, multiply that by the W vector, take the square root, and we get portfolio standard deviation of 4.28%. I'd like to show this to you in Excel. Here's our weight vector, here's our sigma. All we do is we do matrix multiply, and the first thing we want to do is the transpose of the W vector against sigma. And then what we want to do is multiply that against the W vector. One trick to understand, however, is in Excel, you can only multiply two matrices. So you have to actually do it this way. Do another matrix multiplication and then tack on the weight vector at the end. So what this formula is saying is do matrix multiplication, and the first matrix is actually going to be the matrix that results from multiplying W transpose by sigma, and then the last matrix is just the weight vector. Control-Shift-Enter, but remember we need the square root of that. So take the square root. Again, Control-Shift-Enter, and you can see that portfolio standard deviation is 4.28%. What I really want you to take away from it is this. Almost nobody has a portfolio with two assets. There's almost always 10 or 20 or 30 assets in a portfolio. Can you imagine trying to do this math for 10 or 15 or 20 assets? It's nearly incomprehensible. But this, W transpose sigma W, is actually very, very easy and very, very clean. So in summary, we can say that when we're doing portfolio optimization, all you have to do is this. Define your weight vector, define your expected return vector, and define your variance-covariance matrix, which we call sigma. All you have to do then is, in order to get portfolio expected return, multiply W transpose by the mu vector, and to get portfolio standard deviation, take the square root of W transpose sigma W. Once the portfolio expected return and standard deviation are calculated, you can use Excel's solver function to do portfolio optimization, meaning you can either maximize a portfolio's expected return with a set level of acceptable standard deviation, you can minimize a portfolio's dispersion or volatility after setting your desired level of expected return, or you can maximize the Sharpe ratio. Now, one last thing I'd like to show you in the module today, and then we'll be done. How do you calculate the variance-covariance matrix? Because remember, you have to have this variance-covariance matrix in order to do portfolio optimization using matrix algebra. So how do we get the variance-covariance matrix? I would just like to show this to you very simply. Recall that the covariance between assets X and Y is calculated this way. For every period, you take the X observation and subtract its average, the Y observation and subtract its average, and then multiply those two. So if you're doing monthly returns every month, take the return to asset 1, subtract its average, return to asset 2, subtract its average, and then multiply them. Add up all of those products from every single month, and then divide it by the number of months. So that's how you get covariance. So if you want to generate a variance-covariance matrix, this is all you have to do. Begin with a data set that's an n by k data set of monthly returns. So you have n monthly returns and k assets. Calculate the average return for each of the assets, and then for each month in your data set, subtract the average return for each of the respective assets. What that's going to do is that's going to result in an n by k matrix. So if you have 60 months, then you'll have a matrix that has 60 rows. And if you have 10 assets, you'll have 10 columns. And what you'll have is each month, so in each element of that matrix, you'll have the return to that asset that month minus its average return. Call that matrix the excess return matrix. So you'll have an n by k matrix where the rows are the number of months and the columns are all the assets, and in each element of the matrix you'll have the monthly return to each of those assets minus their average. In order to get the variance-covariance matrix, it's this simple. You take that excess return matrix and you just do X transpose X and then divide it by the number of months. So again, you just create a matrix of returns in excess of the average, take X transpose X and divide it by n, and that will result in a k by k matrix, because remember, X is n by k. So X transpose is k by n. So this is k by n multiplied by n by k, which results in a k by k matrix. So if you have 60 months and 10 assets, then you'll end up with a 10 by 10 matrix, which is your variance-covariance matrix. I will actually demonstrate this to you in the next module. But for now, I just wanted to walk you through all the basics. I know this has been a very dense set in terms of material. So we've reviewed portfolio optimization, we've reviewed expected return and standard deviation to portfolios. We've gone through a matrix algebra primer. I've showed you how to calculate expected return and standard deviation of a portfolio using matrix algebra. Lastly, I've showed you how to calculate the variance-covariance matrix. Again, there are no deliverables associated with this module, but in the next module, we're actually going to execute this. We're going to calculate the variance-covariance matrix. We're going to figure out the expected return and the standard deviation for a multi-asset portfolio, and we'll do some portfolio optimization. Until then, take it easy, and I'll see you next week.